Welcome back to Rationalizing the Denominator. Today we're going to be talking about rationalizing with higher roots. So we're not going to just use square roots, we're going to be doing it with higher roots. It was easy with square roots because we could just multiply by the radical 2 over radical 2, and it would eliminate the radical in the bottom because a radical square root times itself twice. Okay, keep in mind that there's an implied index of 2 here. So anytime if we multiply 2 to the first times 2 to the first, we get the square root of 2 to the second, which undoes the square root. So we end up with 2, and that undoes the square root. Now we are talking about higher roots. So we're talking about the cube root of x. So how do we do that? Well, a mistake would be to just multiply by the cube root of x over the cube root of x. And let me show you why that's a mistake. If you multiply the cube root of x times the cube root of x, you get x squared. That's what's underneath the radical, and the cube root of that. The top's fine because we get the cube root of x, and we don't really care about the numerator, but denominator is the one that we're trying to rationalize. So, is that any better than where we started? Definitely not. This is not the way to go, okay, because it didn't get us anywhere. We still have a radical in the denominator. So what do? Well, let's go back to the drawing board. We want the radical to disappear. So what can we have underneath the radical to make it go away? Well, how do you undo something that's cube rooted? You cube it, and that gets rid of the cube root. So ideally, what we want, let me move this over as an example. I'll even change the color. Let's change it to, let's change it to yellow. Nice and visible. How about neon green? There we go. Okay. So ideally, we want this to equal, in the denominator, the cube root of x cubed, because that is something we can take the cube root of. We want to multiply by a term that creates a perfect root. In this case, it's a cube root, so we want something that can be cube rooted, and that is x cubed. So how do we get there? That's the second question. How do we get to that cube root? Well, let's go over here and explore this idea. So if we have the cube root of x, we want to multiply it by something, that unknown, that's going to go here. Let's actually highlight in green. So we're going to multiply it by something, by the top and the bottom and the top. That's going to equal the cube root of x cubed. Now the principle goes back to our first example here. We want to multiply something where, stay here, where the indexes get added together to give you the desired, it's not the indexes, the exponents get added together to give you the desired outcome. So we want a 3, and there's an implied 1 there. Let's use that in green. So what do we have to do to get that 3? Well, we have to add 2. So we want to multiply by the cube root of x squared, because x to the first times x squared gives us x to the third. And if we take the cube root of that, it gets undone. So we multiply by, let's change it to, let's see if in green, cube root of x squared over cube root of x squared. So we do the cube root of x times cube root of x squared, we get cube root of x cubed. In the bottom, in the top, we get cube root of x squared. We can simplify the bottom. It just becomes x. The top doesn't really matter, but that's our answer. We get the cube root of x squared over x, and that is simplified. There's no longer a radical in the denominator. So let's go on to our next example. Here we have the cube root of 27. I like to split it up over the cube root of 16. So we can take the cube root of 27. If you're not familiar, you can always use a factor tree, and the factor tree will tell you what it becomes. So because the index is 3 here, we're going to look for anywhere we see 3 of the same number in our factor tree, and that is 3. There's nothing left over. There's nothing that doesn't have a triple group, so the answer is just 3 to that, and it is a perfect cube. Now we're going to take the cube root of 16. So again, this is cube root 16. We're going to again factor tree to 4. I like putting the prime factors on the left. Again, because the index is 3, we're looking for anywhere we see 3, and this time we have one group of 3, and then we have 1 left over. So what do? These 2's get to leave, or sorry, I don't know why I wrote a 3 here. This is supposed to be a 2. We have 1, 2 leave the house because there's one group of 3 2's. So 1, 2 gets to leave the house, but 1 has to stay inside the radical. Okay, so all we did here is we just simplified. We didn't rationalize because there's still a radical in the denominator, but we did simplify it. So how do we rationalize it? Well, we need to think, what can we multiply the top and bottom by to give us what we want? And what we want is we want there to be a perfect cube in the bottom, so we can take the cube root of it. Well, right now it's 2, and we can't take the cube root of 2, so what could it be? How about 2 to the third? We can take the cube root of that. Okay, anytime we have something like that, it undoes the exponent. The cube root undoes the cube, the exponent, to become just 2. And the reason is the cube root of 8 is 2. What times itself? 3 times gives you 8. 2 does. So in reverse, the cube root of 8 is 2. So how do we get there? What do we multiply by the cube root of 2 to get the cube root of 2 cubed? Well, we need to multiply it by the cube root of 2 squared. Again, we add the powers. Well, we can't, that's a little big, but there's no power. There's an implicit power there, the 1. The 1 plus the 2 equals the 3. 1 plus the 2 equals the 2 cubed, okay? Well, you multiply by the bottom, you have to multiply by the top, cube root of 2 squared. So let's go ahead and multiply our top. And I'll go ahead and use blue. I'll keep it blue. Move this over. So I have 3 times cube root of 2 squared is 4. So I simplified that. Now I still have this 2 right here stays. We leave him alone, but then we already determined that this cube root of 2 times cube root of 2 squared gives us cube root of 2 cubed, and that was the whole point. We wanted that to become that. That's why we chose to multiply by this, which is the same thing as 1 because it's the same thing divided by itself. Now we can simplify even further to get our final answer. 3 cube root of 4, the top is fine, over 2 times cube root of 2 cubed is 2. 3 cube root of 4 over 4. Now, this next example seems like it's tough, but it's actually not that bad. So let's go ahead and simplify it. We get the fourth root of 5x. Now we're dealing with fourth roots and the fourth root of z. So we need to multiply this by something. What do we need to multiply it by? Well, it needs to be in the same in the top and bottom. And we want it to be a perfect root in the bottom. So we already know it's the fourth root. So what is a perfect root that we can take? Well, we can take the fourth root of z to the fourth. So we want z to the fourth to go in there. Okay? I just drew those extra arrows for effect. But what do we multiply z by to get z to the fourth underneath the radical? Well, there's an implied 1. So you think to yourself, 1 plus what gives you 4? And that is z. Let me change the color here. Let's make it, I don't know, let's make it purple. Z cubed. So we take the cube root of that, and we multiply it by the top and the bottom. Oops, not the third root. Sorry. I meant the fourth root. Fourth root. Okay. Now, this is good now. This multiplied together gives you that. That's the whole reason why we chose that. And we chose that because this is going to simplify to be just z. Let me change it to a simplification color. Z. It's going to be just z in the bottom. Now let's consider the top. So we have the fourth root. We can leave the fourth root there and just multiply underneath the exponent, or underneath the radical. We get 5x z cubed. And there's nothing we can do with that, so we just leave it. We can't simplify that any further. There's no perfect fourth roots there. And so there is our final answer. So we're going to put a pause to the video here. We're going to continue with rationalizing denominators in part 3 of this video. It's going to be very short, but see you next time.